Hello everyone. Welcome to this week's ASB seminar. Today we are very happy to invite Tianyu Fu to talking about think as hard selective latent iteration to improve reasoning language models, which is another working related to the loop transformer. Tianyu Fu is a 4 year PhD student at Department of Electronic Engineering at Tsinghua University. He is currently a visiting student at Professor Bailey Chen's lab for 6 months. His research focuses on efficient algorithm for long-context large language models, with interest in sparse attention, multimodal collaboration, and efficient reasoning. Let's welcome Tianyu for today's talk.
Okay, thank you so much, Tianyu, for the warm introduction. Um, and Good afternoon, everyone. Happy Thanksgiving. And yeah, I'm very happy to introduce our latest work on recurrent transformer. And I've learned that there's like many guys here in this seminar that is very familiar with loop transformers, and we I have to say that we are rather new to this community. So feel free to interrupt and ask any questions if you have any problems. And hopefully we are doing it right. Okay. So yeah, without further ado, let's get started. So here's the background. Everyone knows that LLMs nowadays are increasingly used in diverse domains and tasks. And a few Okay, so before we get started, I want to clarify the terminologies we may use. So we're talking about autoregressive generation in large language models, and we split the process generally into two stages: the preview stage and the decode stage. So the preview stage stands for where you take all the input and generate the corresponding KB cache of the input, and the decode stage refers to the token by token generation of the LLM itself. So this work is actually a successive work following our previous work called Roads to Rome or R2R. So the previous work, basically we reviewed that in current LLM generations, like most of the next tokens are pretty much very easy to predict. A similar conclusion drawn also from the speculative decoding community. And we've quantified that how many token is rather easy. And the conclusion is there were like 90% of the tokens where 32 billion model and 1.5 billion reasoning model will reach consensus in next token prediction. And among the 10% different predictions, there are like 5% of them that are actually only 5% of them that are actually divergence. So in the previous work, we essentially built a small large language model collaboration system. We'll go to that briefly. Go to that later. But the problem is, and then we based on the insight and observations from Rose to Rome, we now introduce Think and Heart, which essentially replace the large language model with a iterative loop transformer. Yeah. So let me explain. So in the previous work, as the motivation is that the small language models are fast, but they are very weak, and the large language models they are slow but very strong in reasoning. So is there a way like to combine the advantage of both models? The main insight is just as we talked earlier that most of the predictions from the large and small language models are identical, which means they would make exactly the same next token prediction, during the generation. But um, uh, and among these 11% different next token predictions, we find that some predictions, although they are different, but they are kind of like neutral difference. For example, let's versus let us. And only a fraction of it, which is approximately 5%, is the truly divergent tokens, which means like those examples where the small language model may directly trying to compute a very complex algorithmic problem where the large language model is saying it is hard, so we can like break it down, etc. So here the question is how do we deal with this 5% divergent token? How do we correct them so that the reasoning paths of a small language model can stay on the right track, like those as the 32 billion large language model. So in previous work, we basically switch between small and large language models, where we train a neural eager decider to identify those so-called divergent predictions from the SLM, which is predicted to be different from the large language model and may diverge the entire reasoning path. We train a small router to identify those tokens and then let the LLM to repredict these tokens so that these errors can be immediately corrected and let the reasoning path stay on the right track. However, the problem of this previous work is also so in the previous work there's some speed ups and accuracy gains. It has a nice parameter accuracy trade-off, which is reaching a new Pareto frontier compared with distillation and query level routing. And it has practical speed up compared with the distilled RY models. And we also have a demo here. So for anyone who is interested, feel free to check our open source code and the demo webpage. Sorry, I see a few. Okay. But the problem is, even though we kind of like let the small language model follow the large language model's reasoning path in this previous work, the problem is we still need two models. That means we still need to load the large language model onto the GPU. So it still takes additional weights, and also it has to maintain separate KV caches for the small and large language models. So it's kind of like it has the speed up, but it still burdens the memory system. And memory, GPU, high speed memory, especially edge applications, it's kind of like a valuable resource. For example, in your smartphones, the memory size is very limited, and even on GPUs, there's limited size of the of high bandwidth memories. So, and it's very expensive to manufacture those memories. It takes a lot of wafer how is it space to manufacture those memories. So the thing we want to solve at this think of hard work is that we want to examine why those small language models cannot perform well. So can those can the certain hard token predictions be done without adding additional parameters? And the recent advances in loop transformer just give us confidence that it tells us that you can just iterate through the same parameter, and then you may have the chance to achieve a better prediction. So essentially, we want instead of introducing another language model, another larger language model, we want to use the exact same small language model, but we want it to iterate multiple times on those hard predictions so that those hard predictions can be corrected and hopefully gain a better prediction over this single pass prediction. So that is basically the whole idea of the work. But after like actually digging into it, we found something that is unexpected, which we call it the latent overthinking phenomenon. So what we do here is that we investigate the predictions made by the loop transformer at each iteration. So we do this by like checking whether the language model already made a correct prediction at the first iteration, or it has to be is it only possible to make those predictions at later iterations. We do this by examining the intermediate outputs from a uniformly, we call it sync twice variant of loop transformer, where each token is looped twice before it make the prediction. And what we find here is that although the loop transformer can correct some errors that exist at the first iteration, it also involves some errors. So just like the overthinking problem in regular transformers, where uh, when you output more tokens, when you investigate more computations, the results is not necessarily better because you may correct. Sorry, you may falsely predict, or you. Sorry, let me rephrase. You may revise some initially correct predictions into wrong ones if you are overthinking. So this phenomenon also exists in the latent uh, thinking realm, where we find that there are. So let's look at this figure. Um, Among all the predictions, there are 82%, 83% predictions the model always get it right, no matter how many loops it goes through. And there are 12% of the predictions where the model always get it wrong. But among those predictions where model made different, among those tokens where model made different predictions at its first loop and the second loop, um, there were actually 57% of the predictions that was initially correct, but is revised into wrong ones at the second iteration. But there were only 43% of the tokens that were initially wrong and revised into right ones. So that means by iterating a second time, the model is actually making more false corrections than the actual beneficial ones. So, of course, this is a specific behavior of a Queen 3 model on this specific data set. But the intuition here is that can we like loop in a smarter way so that we only think harder at those essentially harder tokens that we dedicate second iteration of latent transformers to revise those hard tokens instead of like evenly distribute this computation so that and introduce this overthinking problem. And the Oracle experiments shows that this idea might work if we can really precisely identify where should we think twice. So this is the Oracle experiment in our paper, and the standard ones stands for those like standard transformers where no latent loops are introduced. We just forward ones to predict each token, and this always think variance means that it loops twice for every token. And we introduced this think out hard oracle where we only let the language model to iterate twice if its initial prediction is wrong. Know that this oracle signal is not acquirable during actual generation because you never know whether your first round generation is correct. But if we provide this additional signal to guide the iteration depth, you will see a very noticeable accuracy gain on the mass benchmark. So this motivates us to explore the question of can LLMs selectively dedicate latent iterations only to hard tokens? And there are a few challenges regarding this objective. The main challenges are respectively model architecture and training scheme. So let's go with the model architecture first. The first thing we want to deal with is that how we support dynamic iteration depths. That means two things. One thing is that we want to enable cross-depth information flow because some token iterates deeper while some tokens stop at shallower iterations. So if these tokens at different iteration depths cannot exchange information, it means you lose your context at some iteration depths. So the first thing we want to do is we want to enable a cross-depth information flow. And the other thing is that while previous work, they allow this information flow by taking advantage of all the iterations. It introduced the problem of they break the parallel computation required for training and prefilling. So So yeah, that is the two things we want to deal with. Um, and previous works, they normally take the choral attention, the standard choral attention, where each token just attend within the same iteration depth, or they simply attend to the first iteration. So it is fine if you are talking about a uniform depth loop transformer, but it introduces problem in this depth setup, because as you can see on the right figure, if some because some tokens iterate deeper and some tokens stops at shallower layers. So if you only attend to the token at the same iteration depth, you lose its context. For example, this green token cannot see what its previous token is if they only attend to the same iteration depth. So let me see. Yeah. Um, so the solution we provide is that we try to extend the causality of regular choral attention to a 2D space, where each token is allowed to see its previous positions and shallower iteration depths. And from the WeChat group, we discussions, I noticed that there's a kind of like a previous work where we previously thought it was like exponentially growing. We thought it has exponentially growing complexity with respect to iteration depth, but it turns out it still has a linear growing complexity. So it's very similar with the solution we are proposing here. But I want to explain that this dual choral attention, it tries to perceive the question from the chorality perspective. So in theory, dual choral attention can do prefill in a full parallel way, not only at the sequence length dimension, but also at the iteration depth dimension, as long as you can provide proper input of these dimensions. So in theory, dual choral attention is a full parallel solution where you can generally extend chorality to any dimensional spaces and ensure full parallelism along those dimensions. Yes, and the second thing is that current loop transformers, they use identical weights across all iterations. This is something we find not necessarily optimal, because there's an obvious objective shift among different iterations. So we all know that the standard transformer do the next token prediction at the first iteration. So when you, and by the way, the background of this work is that we do not want to retrain the whole model. We just want to fine tune from existing standard transformer to its loop transformer counterpart. So it means if we are using the identical weights across all iterations, the initial behavior of this transformer will be predicting the next token at its second iteration, right? Because the first iteration already predict the next token, and the output is giving us input of the second iteration. So by iteratively doing so, it is essentially predicting the next token. But that is something we do not want. We want the transformer to kind of stop and rethink and refine its current prediction instead of predicting further ahead. So you may notice this kind of like objective shift between different iterations. And to facilitate such objective shift, previous transformers rely on identical weights, which is kind of like hard because, yeah, the objective is different. So building on this idea, we simply introduce LoRA to deeper iterations to facilitate such transition in objectives. And also there's, yeah, and also we follow previous work to use residue connections because it makes the gradient flow better, easier, and the learning objective also easier because the later iterations essentially learning a residue that is added towards this current iteration. So in summary, the first iteration simply do the next token prediction as in original transformers, and the later iterations, they shift the objective to current token refinement that is specifically targeting at hard tokens and refine the predictions. Yes, and also we follow the previous work of Rose in Rome to introduce the iteration decider, which is actually a simple NLP. And the goal is to decide whether to continue latent thinking or just stop and output the verbalized token after each iteration. And we take shallow, middle, and final hidden states from the backbone to make such predictions. And actually, it's the reason why we use such an easy and small architecture to facilitate iteration decision is that it's actually a rather simple job, because we find that when models are making confident predictions and incompetent ones, their internal states just differ drastically, especially their entropy and especially their entropy. And also, it has a strong correlation with the token frequency. For example, if it's predicting a rare token, it is highly likely that its prediction is different from the large language model. But if it's predicting a commonly seen token, that is highly likely that it's not divergent. Okay, then finally the training scheme. So basically the backbone LLM and the neural iteration decider are actually two tightly coupled components. Because the backbone LLM, it generates the hidden states at the input to the iteration decider. So it basically tells the iteration decider whether the LLM is confident at the current prediction. And the iteration decider it's to take this input and decide whether we should iterate twice. But if we were to train it jointly, the problem is if the iteration decider decides to always iterate at every token, then the backbone model would not need to provide a reasonable prediction at the first iteration. It just has to do it right at the final prediction, which means it alters the landscape of this LLM. And in turn, if the backbone model decides to, say, do the right prediction within each iteration, so at its first iteration, then the iteration decider just simply stops iterating and verbalize output at this first iteration. So you can see that there's a tightly coupled scenario where the quality of backbone model influence the policy of iteration decider, and the iteration decider policy also in turns influence how the backbone should behave. So because of this tightly coupled relationship, it's very hard to simultaneously train both components. And actually, we are adopting a rather simple but effective solution here. That is, we let the backbone model and the iteration decider to sequentially train, and they both align to an Oracle iteration policy. The Oracle iteration policy is the policy that we discussed earlier, where we only think twice if the LLM cannot make correct prediction at its first iteration. So this is indeed it's perhaps not be the optimum policy, but from the previous Oracle study, we can find that this policy indeed performs really good in real life because it's pretty much the desired behavior where you only iterate twice if you cannot get it right at the first time. So thanks to this policy, this training become very stable and scalable, because essentially what we're doing here is we label which tokens are easy and which tokens are hard using a supervised fine-tuning variant of the base model, depending on whether it can make correct predictions on each token. And using this label, this label is just for brevity, we call it the iteration Oracle policy pi. And we use this Oracle policy pi to control the iteration behavior of the backbone model during its backbone training. And we only apply the next token prediction loss, the standard SFT loss, on the final verbalized token of the backbone model. which means we do not supervise those intermediate hidden states of the loop transform. And the second stage is that after the training of the backbone model, we then align the iteration decider to the same alpha policy using the input from the frozen well-trained backbone model. So it's a kind of like two-stage training, and it's very stable and easy to implement. So finally, it's the experiment. We primarily test on Queen 3 series, all training from the base model. We recently add the 4B variant of Queen 3, but the result is basically the same. And also we compare with few baselines, including the standard ones where you always iterate once, and the overthink variants where you always iterate twice. And also the soft think, which is a previous kind of like latent thinking counterpart, and also ponder, which is not listed here. And note that because we add the LoRA weights and also the iter decider, so the weight of the model is slightly increased, 3%, compared with its standard variant. So in order to make a very fair comparison, we also prune one layer out of the main model to ensure that our variant has exactly the same or a slightly smaller parameter size over the standard variant. And the one that is not pruned, we call it TAH plus, which includes 3% extra parameters. And here's the basic results, and we test across all kinds of math problems. So we train about our math problems, and we test other challenging math benchmarks. So it shows that the equivalent parameter variance, that is TH, achieves in general 4% to 5% increase of accuracy compared with the standard variant. And the TH plus, which introduced 3% additional parameters, generally achieves like 5% accuracy improvement. And we also actually added a general trained version of TH and test like coding and question answering benchmarks, which will be updated soon. And these the results just confirm with what we have found on the math benchmarks. And there are two things I want to mention. The first thing is that TH actually shows much lower cross entropy loss during its training compared with the standard variant. So, but of course, this lower cross entropy loss wouldn't necessarily translate to the final accuracy gains, because during training we're using an optimal oracle policy, but during training we're relying on the iteration decider, so there's a small gap there. But through the training dynamics, you can see that iterating only on those hard tokens actually really help the model to converge quickly and reaching a lower entropy. And the second thing is that the iteration decider is actually very robust to the so-called continuation threshold. Sorry, I forget to introduce that. So for the iteration decider, it basically predicts the probability of continuous iteration or stop and verbalize. So it's outputting a kind of like probability, and we use threshold to convert this soft probability to a hard decision, where if your continuation probability exceed the threshold, then we continue. If else, we stop. So if we are altering the continuation probability, we are essentially altering how much token should be, how many tokens should we think twice. And as you can see here, we are kind of like changing across a vast range, where the continuation proportion ranges from 0 to like almost 41%. And but the model itself is pretty robust to this change. This is because we're using the adaptive LoRa architecture where we try our best to preserve the strong next token prediction ability as the first iteration. So we are only doing additional refinements on the second iteration, so it won't hurt the original ability of its first iteration. And also we did the ablation study to show each design factor's uh, effectiveness. So as you can see, the LoRa architecture, the residue connection, and the dual tension architecture both contributes to the increased accuracy. And also we did a little bit ablation on the training scheme where so we try to supervise the output token only, or we supervise the output token plus the latent token during each loop. So under our structure, on our think and hard philosophy, it's better to just supervise the final output because we are using the oracle policy so that we do not need to worry about its first latent iteration. And also, we try other iteration behaviors during training. So, but it turns out our policy provides a more robust and preferred results. Yeah, and this is our first journal we talked earlier. So as you can see here, now we are only getting like 5% increase over the standard counterpart. But if later we can truly do it right, we can make these perfect or near perfect iteration decisions. The ceiling of the possible accuracy gains is quite high actually. And the other thing is that we also try to examine the behavior of this model. So we want to understand which tokens are most likely to iterate twice and what corrections does the model make during those iterations. So it turns out that the most tokens that iterates twice is the connectives, logic connectives like but and so. As you can see, it's pretty important because when you say but, you are essentially changing your direction of reasoning. But when you say so, you're actually continuing to the same direction. So it's quite important where the later iteration will goes. And as you can see here, if you predict but in the first iteration, there are 11% of the cases where the model shifts but to so at the second iteration. So and also if you predict so at the first iteration, there are also 6% possibilities that the model shifts to but. So as we can see, the model is quite not sure whether to continue or keep thinking about the same thing at its first iteration. But these predictions it's getting better at its second iteration. Yeah, and that's pretty much everything we talked about. And all the codes are open sourced, so you can find the code at T2NSS GitHub repo, and you can see this is the work we discussed about, and this is its previous work and also some other works if you are interested. So I think that's all. Thank you so much.
Yeah, if anyone has any questions, feel free to type in or just unmute yourself. Yeah, maybe I can first ask one question. It's about I see the interesting design of the dual-causal attention. Yeah, I was wondering that the first thing is that you still use the standard position embedding, the 1D position embedding for this setting.
Yeah, that's an excellent question. In theory, we should use a 2D positional embedding, but in this case, we just follow the original setting and use the 1D one
I
because
see.
we are actually having the LoRa architecture at the deeper iteration. So LoRa actually already facilitate these, or already help embed the iteration depth information. So we can use the 1D embedding. But if you do not use the LoRa design, I think it's better that you switch to a 2D positional embedding.
Yeah, and maybe another related relevant problem is about I think that due cultural attention may increase the complexity, the computation. Yeah, what's your idea on this part?
Yeah, that's also an excellent question. So we can see this figure regarding how we actually compute this. Let me see, where is it? Sorry, one sec. Mhm. Yeah, we can see this figure.
Yeah, yeah,
So, so this is how we actually compute dual attention. This is the exact same example we're making here. And basically what we're doing is that we store the KV cache of respective iterations separately.
yeah.
And then during attention computation, we simply concatenate those KV caches by iteration depths. And then we apply a specialized attention mask to enforce the due correlation, where within each iteration, with at this block diagonal, it is just standard choral
I
attention.
see. Yeah, this makes sense. Yeah.
Yeah, and at these non-diagonal blocks, they are actually also choral, but it's not a standard one. It's just like you are skipping some rules
Yeah,
essentially.
yeah, yeah. This makes sense.
Yeah, so this kind of pattern is actually easily supported by those like flush transformers.
I see.
Sorry, flush retention and existing frameworks.
Yeah, yeah. I see. Yeah, this makes sense. Yeah. Thank you. Yeah. I think
Thank you.
maybe Jeff has some problem.
Yeah. So I had a question about so I mean you've done several ablations, but one that like you didn't do was, or maybe you did, was to just use a confidence only baseline where you train the decider just on confidence, or in the other way, only on the logits, right? So you could just train an MLP to predict the Oracle continuation labels just based off of the layer features, the hidden states. And I was wondering, like, and quite frankly, there's a very big design space in terms of like what features you include. I wondered if you had any thoughts on that generally.
Oh yeah, so that is also an excellent question. Um, I think I want to answer this from the results of our previous work. Uh, Let me see. Sorry, one sec. Uh, okay, let's see this one. Yes. To begin with, there are indeed some like oracles that showing which metric is most useful to predict whether this token is needs to continue or not. And the most obvious one is the one you mentioned, the output logits, and to be specific, the output logits entropy. It is indeed a very great indicator. As you can see here, if we plot the entropy distribution of those hard tokens, and sorry, by hard I mean those tokens that we need a second iteration. So when we're plotting this distribution, you can see there's a quite distinct distribution shifts between hard and easy tokens. So it's indeed a good logic, a good metric, and we do try this. And the result is it kind of it is slightly better than the standard variant, but it's not as good as the neural one that we are currently adopting. Because although entropy is a very good metric, it is not the only one that is affecting whether the code is hard or not. So in terms of which things are most influential regarding the hardness of the token, we kind of like explain it in the previous book, Rose to Rome, where in addition to entropy, there's another important factor that is the token frequency. So in this figure, the x-axis is how many times this token occurs in the training set. For example, like me, but so it occurs frequently. But some tokens, like the name of some chemical components, they appear like seldomly in the training set. So that's the x-axis, and the y-axis is actually how we can think of it as uh, how likely is this token to be hard event. So how likely that this token is hard? So as you can see here, if the token appears rarely in the dataset, then it's more likely to be hard. So this is actually another important oracle. So that is why we are using a neural one to take the hidden states, because the last layer hidden states contains both the information of largest distribution and that corresponds to entropy, and also the next token prediction result that corresponds to the token frequency.
Mhm.
Yeah.
Cool. No, thanks for that. And like I was saying, I think there's probably a very big design space in terms of exactly like, I mean, essentially you could do feature engineering. Maybe you looked at a bunch of other stuff as well that didn't work. I'm just curious, like, so like, output, so entropy distribution might be one, but like, I could imagine all sorts of different other features. Did you try any others that like you thought might work but didn't, or?
Yeah, great question. Oh, by the way, sorry, I forgot to mention one thing. So in our paper, we actually take not only the last layer hidden states but also the largest. Despite these two things are essentially similar things, their difference is only a linear transformation of the LM head. But these two things are actually both essential because when you because we're using a small neural decider, so it cannot have the same capacity as the large vocabulary embedding metrics. So it's essential that you simultaneously input the last hidden states and the largest to the neural decider empirically.
Mhm.
So if we only give the last year hidden, if we only give the last year hidden states, it cannot make such accurate predictions.
Cool.
Yeah, but this is all done within the current small size parameter. So I think if you are increasing the iterated decider's parameter size, it should be enough to just give the last year hidden states. But yeah, currently it cannot. And also we tried something called let me think what it's called. I think it's called sorry, one sec. It's called, certainty. I think it's called self-certainty or something. It's also
Oh,
another
self-consistency?
um I think so. It's kind of like another metric that is transformed from the logic distribution that describe the logic distribution. Logic
Mm.
distribution. Yeah. Like for this metric, um they pretty much like behave similar as the entropy metric. Um, but indeed there are like few tokens that it cannot essentially distinguish because yeah.
Well, I'm sorry. Oh, actually, maybe we didn't get to this, but like I was really curious, like what about the so uh obviously output logit distribution is super important, but what about the hidden states that you're adding in? How important are they? And so in other words, like would it work to use just hidden states without like logit entropy or without confidence?
Yeah, we didn't do the ablation in this work, but you can refer to this simulation study
Hmm.
from R2R. So you can see here we try different combination of inputs, uh, and but this is not all the combinations. But I think if I were to rank, the most important thing is logics, and then hidden states, and then which token you are actually sampling.
Hmm.
Yeah,
Okay,
as
cool. Thanks.
thank you.
Yeah, maybe I have also another question that how do you think that because I think that in previous loop transformers that people will not limit it maybe two turns that they will have multiple turns here. How do you think that maybe the method can enable more aggressive adaptive just means that there are multiple rounds?
Yeah, that is also an excellent question. We did try to loop 3 times. Let me see, where's the result? Mm, yeah. So yes, so in this turn, we expand the maximum depth to 3 times, and it's indeed slightly increase the average performance. Uh, but I would say the benefit is not that obvious, and it poses a lot of challenge in our training system.
Yeah, yeah, yeah.
So,
I think
so we
that there
didn't,
are some challenging training to scalable. Yeah, in this
yeah,
way.
so we didn't examine that much. And the other thing is that if you are talking about multiple iteration depths, you have to design a metric for so-called hard in terms of iteration depths, because now it's just a binary concept. But
Yeah,
if you're
that's
talking about multiple, yeah. So we did do that in this work by by kind of like using multiple models to, if they both think this token is hard, then it's indeed hard. But if they like some of them think it's hard, then it's probably just need to iterate once.
yeah.
Mm, yeah, but I think it's a great direction that we iterate deeper, and I think it will be better we do this uh, and we build upon an existing architecture that already show good performance when we iterate deeper. Because in our experiments, I think um,
Yeah, I think that's quite interesting because I see that in one previous loop transformer paper, I forget, maybe I do not know exact name. They also do the math task and they maybe loop more times. But what is interesting is they find that deeper the loop, that they also see that the math 500 that drops performance. Yeah. Yeah, but others keep to improve. Yeah, I think that on challenging tasks like Olympic bench and AME 25, that increasing still achieve no just non-trivial improvement. Yeah.
yeah, yes, that is also that is also something we observe. So I think loop transformers are really good at reasoning tasks, but if it involves like knowledge, it won't help even if you loop high, if you even if you loop deeper.
Uh, and I think that the third round, the third iteration still use a different LoRA compared to the second one. Just means that they are separate parameter.
I think we try both settings and the results are pretty much similar.
I see. So I
Yeah.
jumped that the first round is different, but later one's similar to be similar. I see. This makes sense.
Yes. 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 It's especially in our setup where we fine tune from an existing model. So it's pretty much very
Uh,
yes. But I think the landscape may be different if you train from scratch.
And I think, and do you think it's very important to manually that to decide what is hard, yeah, for what is not hard, just means that which token needs more iterations? Because I think that many loop transformers they just enable just means that they implement the gate, yeah, but they just let the model itself to learn that which need to route more times, yeah, instead of that have some maybe supervision from the data itself, yeah.
Yeah. Yes. I think it's an excellent question. From my experience, I think it's important. It's very important if you are talking about fast convergence, because the design space is very vast, and like I said, they have like joined. They influence each other. So we try to let the model itself to decide how much time it should iterate. It turns out the loss curve is essentially a similar one as the standard transformer. So it's in terms of convergence speed, it's not good to let the model itself to decide. Um, and the other counterpart is that we use other metric to define hardness, and we do try to use kind of like cross entropy. We'll try cross entropy, entropy, and the current one that is top one, a difference. Um, either so these let me see where's the result. Yeah, here's the results. So yeah, this is the one. So as you can see, cross entropy and our current implementation basically perform similar. But
I see.
entropy, yeah, but entropy is not a very good standard that may achieve like similar loss with over the standard pipeline, over the standard one.
I see, I see. This makes sense. This is interesting.
Yeah, but I think indeed the kind of like the hard label is a very important thing. And admittedly, our current label is not perfect because as you can see here, if we observe the iteration behavior, some of the corrections are not meaningful because if you are changing but to weight, it's not that meaningful because it's essentially but weight or weight, which means the same thing.
I
So
see. I see.
yeah, I think it would be better if we could use a kind of like a semantic richer way to label those differences or hard tokens.
I see. I think this makes sense. Yeah, and this is very reasonable.
Yeah, thank
I
you.
see. Yeah. Is there, thank you very much. Yeah. Is there more questions? Yeah. Okay, I think that if there's no more questions that we can end here today. Yeah. Thank you very much for Tianyu's talk today.